Cioè, ma pronti quando... Allora?
Final lecture of Giulio and the final lecture of the school. Thank you so much.
Okay, so when we started the set of lectures, I promised you to discuss differential equations of mathematical physics, but we still to generate them. So they arise indeed by particular limits of BPZ null state equations, which we now review ultra shortly. So a null state is a state which sits in a representation of Virasoro generated by some primary state after I lift it of some steps in the level, and then suppose I get a state after k steps, which is again a primary. And so the representation, instead of being irreducible, is irreducible. Then this primary state will become, has to be projected out, and indeed is a null state in the theory. This does not happen for any value of the conformal dimension, but it happens only for particular values of the conformal dimension. So now let's do the classical case, kappa equal to 2, which is the first non-trivial case. So in order to find the value of this dimension, we have to go back to the gram or chapel of matrix that we were discussing, and put to 0 the determinant of this chapel of matrix truncated in the block corresponding to the number of steps, so block at level 2. Now this matrix in the parameterization that we like is given by kappa at level 2 is given by this formula. It's symmetric, of course. And so putting its determinant to 0, we find that the dimension has to be given by this formula. Okay, very good. So this is a phenomenon which happens in any conformal field theory. And if the range of the parameters is, if this equality between central charge and the actual spectrum of the possible conformal dimensions is realized, for the field theory it always realizes, because the conformal dimension runs continuous. And good, so this can be solved, and we stay with an equation which says that the two descendants of our primary field, so the two vectors which were composing through the brackets the Gram-Shapovalov matrix, have to be proportional one to each other, okay? L minus 2 of delta and has to be proportional to L minus 1 squared of delta. Okay, so in terms of the field, the local field which creates this primary field, this means that the second derivative of z of the field, phi delta, has to be proportional to the factor of b squared to the normal ordering of the contraction to the normal ordering of the contraction of the field with the stress energy tensor itself. Okay, in Z, in Z. Okay, let's put the Z here. Okay, very good. So this is an operatorial equation in the sense that it holds in the correlation functions, and so we can take our primary field, our degenerate field, which let me not call phi, but at this point we call it psi. So psi becomes degenerate, and we can consider, therefore, together with the word identity of the stress energy tensor, the following equation, which holds for, sorry, here there was a minus 2, which holds for the correlation function of this field with n other primaries. Okay, so now we have a quadratic differential equation, but which has some mixing between the dynamics of the position of the degenerate field and still the position of the other primary field. So the game we will play is to a semi-classical limit, a particular semi-classical limit, in which this dynamics will be frozen. Okay, and the freezing of the moduli of the problem will leave us with a Schrödinger-like equation. Okay, so this is the game that we are going to play. Now, if I want to understand, now at this point, I mean, one understands very well the meaning from the viewpoint of the differential equations, the meaning of the fusion rule between the degenerate Virasoro family, the degenerate Virasoro primary field, and a generic one. Indeed, there is a classical exercise. You try to understand what is the behavior of the OP between psi z and phi delta of z1 by studying the initial equation of the initial equation related to the local expansion. Here, that let's say you take z minus z1, so k times phi delta prime in z1 plus higher order terms. Okay, if you study this, you can identify who is this parameter kappa, which is because of, let's say, conservation of conformal weight given by delta prime minus delta minus small delta, which is the dimension of the primary state, sometimes called also delta 2, 1, because it is the first of the minimal model series.
So this is the one that you call kappa. That's fixed, right?
This is yes. This is delta 1. Okay, depends on the sign of the two. Okay, this is or delta 2, 1 or delta 1, 2, depending if you, okay, there are two solutions. Very good. In terms of moment, okay, we go there. Okay, so now you throw this local behavior inside the equation and you discover that the index kappa has to satisfy the initial equation of the I mean, the consistency condition for this expansion to hold, which is given by the equation 3 kappa minus 1 divided by 2 delta plus 1 minus capital delta plus kappa equal to 0. Okay, and this in the end tell us that delta prime, so the objects which are sitting on the right, can take only two possible values, which are corresponding to the fact that, okay, using notation in which I write the delta of alpha in terms of the momentum, like q squared plus alpha squared, sorry, 4 and 4, delta prime corresponds to delta in alpha plus or minus b over 2. So the momentum flowing from, the momentum of the carried by the degenerate vertex flows in the after diffusion to the right, and the intermediate and the diffusion between the prime generic family and the null one has only two channels corresponding to the two solutions of this differential equation. Okay, so these objects now are particular cases of the vertex operator that we said we can compute with multi-instant on counting, because it corresponds to a particular quiver theory in which at a certain point I insert this strange particular kind of primary field. So we shall understand what happens to the theory we have this kind of particular fields. Very good. So let us do the following. So suppose that I consider this object with 4 insertions, okay? Let me write b of infinity. Let me put the label infinity, okay, t 1 psi z. I put it here just not to have it around in this part of the blackboard. And now, okay, this is a solution of some given differential equation, which is that one with 4 singularities of this type. Now suppose that I want to go to a case which I would be able to solve better. Okay, so a case which I would be able to solve better is the analog of this, where I don't have this singularity. In this case, the differential equation has just 3 singularity, and so it will become an hypergeometric equation. Because in the absence of this, further vertex, the equation does not contain these parameters, these derivatives, because they are all the moduli are fixed, and so in the absence of this, I have this object is the hypergeometric function. Very good. So now what happens is that here I can generate from this function the situation in which this vertex is absent, just by mapping t to infinity, keeping all conformal dimensions fixed. Okay? So if I do this, then here I just sum the two momenta of these vertices, and this becomes an hypergeometric function. Okay, hypergeometric function, remember that it was our toy model. So this is vortex counting. So two-dimensional physics. Very good. So let's now interpret this from the gauge theory viewpoint. We had the gauge theory. This is n equal to nc equal to nf equal to 4, equal to 4 gauge theory. And what we are doing is that we are engaging, setting t to infinity. Okay, so we are engaging the gauge group. So it means that when we turn on this kind of thing, there is something else which is sitting in the theory. No? We have to understand this, the insertion of this primary, as the insertion of some operator in the partition function of the gauge theory. So since here I'm staying with an hypergeometric, which talks with the 2D theory, with the 2D physics, I expect that this still talks to the 2D physics in the gauge theory. Indeed, it has to correspond to a surface operator in the gauge theory, and it does. So a surface operator is an object which is an operator that I can insert in the gauge theory partition function by specifying, let's say, suppose that my surface operator sits in some plane in the Euclidean system I'm playing with, and in the transverse direction where this plane is said, let's say, by in equation z equal to 0, the local behavior of the connection is that of dz over z times an element in the Cartan of the gauge group. Okay? So this surface operator then breaks the gauge group down to the quotient with the commutant to the element I'm turning on. So in particular, let's take the easy case because it's the one that we have to study here, SU2. SU2, you can break with the only Cartan you have down to U1, and so the leftover gauge symmetry is this one. The space of vacua where this parameter can take place is this one. This is just e più 1. Okay? So this is the space of moduli turned on by the surface, which can be turned on fixing the surface operator. Now, the theory calls for a natural coupling of the 4D gauge theory to a 2D theory describing the degrees of freedom of this surface operator, and indeed this P1 is done by South Pole and the North Pole, and the part of the partition function corresponding to the surface operator will become in the decoupling limit exactly a vortex-anti-vortex combination, one for the North Pole and one for the South Pole patch. Okay. So now in terms of the picture we had in mind for the reduction to the cyber-Witten theory, things are going in the following way. So we said that the partition function of the 4D theory is given by this object. The partition function of the 4D theory plus the surface operator is given by this. So now these objects, they have their interpretation as, I want to discuss this in the in comparison with the infrared, I mean, towards the infrared limit, so recovering the cyber-Witten theory. This is this other object. Now I claim it has an asymptotic behavior like that. So you have still epsilon1, epsilon2, F. Now let me turn on a subleading order term. Notice that this is not the same in the numerator, but the leading order it is, because the leading order where epsilon1 is, goes to 0 is, sorry, where epsilon2 goes to 0 cancels the momentum of this surface operator. The next to leading order is given by some object which depends on z, the location of the surface operator, and still to epsilon2. Okay. So to generate the natural object to compare with the surface operator, you have to normalize. I define the wave function of the surface operator to be the normalization of z for d plus 2d over z for d. And this object, you see, behaves like e to the minus 1 over epsilon 2 w plus, I don't know, okay, plus corrections if I put here epsilon 2 equal to 0. Okay, so this is epsilon 2 equal to 0 plus corrections. Now we want to understand who is this leading order in the epsilon 2 expansion of this object. Now, before the limit is taken, the wave function satisfies the BPZ equation. okay, which I write in operatorial format just to make it short. Okay, and now we can take its limit to epsilon 2 going to 0, and this corresponds, which corresponds to the limit in B. Let me write down here. I have in mind epsilon 1 equal to h bar B, epsilon 2 equal to h bar over B. So I'm restating an overall scale in the parameterization, which is usually put to 0. And so I find that there is a WKB-like expansion, which tells me that the leading order term in the expansion of the wave function satisfies this equation here, where phi 2 is the leading order term that I find expanding to the first leading order, the insertion of the stress energy tensor in the equation. Now, this you remember that we identified with the object which defines the Seiberg-Witten curve, and indeed we are finding that so our W is nothing but plus minus the insertion from the start to Z of root phi 2 of Z. Okay, so this is the interpretation of the wave function of the surface operator sitting from a reference point and elongating through this kind of Dirac string to the point Z, okay, because we wanted to be able to move the surface operator around to in the Gayotto curve. Okay, so these two possibilities again they correspond to the two channels in the OP that we had in mind. Now, in the M-theoretic cartoon picture, you remember that we were saying that we had two M5 brains sitting in the direction corresponding to the base of this local K3 and sitting in both the complex direction of space-time and not sitting in the R3, which is transverse to everything. Now, the surface operators are obtained by considering M2 brains, which are sitting only in one of the directions here, and breaking the SO3 R symmetry to SO2, which is the R symmetry of the surface operator theory, which is n equal to 2. Indeed, these are 1/2 BPS surface operators in the gauge theory, and notice that of course since they are not elongating in this direction, they are points on the curve. Very good. Now let's make an equivalent cartoon, which is the following. Now we have to push a bit. So we represent the gauge theory with the brain, NS5 brain setup. So suppose that I picture a Nanani-Witten brain setup like that. These are NS5 brains. These are limited D4 brains sitting between two parallel ones. Now I write points to be gested at 0 and 1, so the elongation of the only of the location of surface operators, while the rest of the space-time is understood to be given in some other color, because we don't have 4 dimensions to make these pictures. Good. The surface operator is a D2 brain quitting orthogonally the blackboard, and in an M5 brain story now I try to be even more brave and bring this picture to lift it to M theory. The situation goes like that. So this is my first M5 brain. Then I have the second one, where this ends. Okay, very good. And then there are M2 brains, which are quitting and ending on this overall M5 brain. This is the covering, is the picture of x squared equal to phi 2 of z, where now I'm specifying to the theory which has SU2 gauge symmetry and no matter. There are no semi-infinite brains outside here, and just two suspended D4 brains. And so the idea is to picture the case in which phi 2 of z is equal to 1 over z squared times u plus lambda squared z plus 1 over z. Okay, very good. Which is the case for the pure gauge theory. Now, we can obtain this result also, the result of reducing the negative partition function to hypergeometrics in some very physical way, which is the following. So let's go back now to this picture. So this is this corresponds of having the full gauge theory coupled to the surface operator. Now, suppose that instead we want to discuss the case in which we generate this surface operator by decoupling from a given from the gauge from the NF equal to 4 NF equal to 4 gauge theory. Okay, so in this case, the brain picture to consider is sorry, let's not align them yet. Is something like that. Okay, here again I have D4 brains, but there are also semi-infinite D4 brains corresponding to the two fundamentals and the two anti-fundamentals. So what shall I do to generate this surface operator? Well, I have to be able to bring out of the blackboard one of these NS5 brain to generate a situation in which I don't have a running gauge coupling anymore, or in particular in which this D4 brain comes at the same strength as the semi-infinite ones. So in order to do that, I have to align the external branes to the internal ones. So in order to do this, I have to fix two alignment conditions, which corresponds to entering the flavor locking phase of the theory, okay, and finally X, the theory bringing out the NS5 brane. The object which stays suspended between the NS5 brane which quits the blackboard and the forebrain which stays in the blackboard is a D2 branes. There are two possibilities to do it, one above and one below, which corresponds to the two channel of the OP. Okay, the two possibilities for the surface operator. Very good. This can be done explicitly looking at the formula for the Nekrasov partition function. Indeed, okay, I make it in Word. You remember that the matter contribution corresponds to some numerators in the formula for the Nekrasov for the instanton part of the Nekrasov partition function. Now, in order to make the engaging, I have to prohibit all young tableaus of one. I mean, I had two young tableaus, Y1 and Y2. Now, to go to hypergeometrics, I shall, let's say, force one young tableau to be the empty one and force the other one to be a single column. Okay? This corresponds to the combinatorics of the hypergeometric, which is just given by products of Pochammers. Okay, so I can obtain the alignment conditions plus epsilon corrections by imposing these two rules out of the numerators in the instanton counting formula. We don't do this exercise because it would take a bit too long while we wanted to finish reviewing a bit of background materials before being able to have a cleaner application of the thing to differential equations. Very good. Okay, at this point we shall understand another concept, which is the one of okay, what is the CFT dual of holomorphic decoupling of matter in the supersymmetric gauge theory. So you remember that we were giving the recipe for the AGT dual for superconformal theories. But then you can turn on masses and you can send masses to infinity, redefining the gauge coupling. Okay, this is the way in which you usually integrate out matter and you generate theories with which are not conformal anymore by decoupling some sectors. Okay, so we want to understand what is the analog of this procedure in the CFT. Now the claim is that we have to invent a new set of states, which we are usually not. I mean, we usually don't study in the classical text in conformal field theory, which are the irregular vectors. Now, irregular vectors are obtained by taking primary fields and colliding them one against the other, rescaling in a particular way the conformal dimensions. Okay, so you remember that earlier we were throwing one vertex against infinity, no? To do the decoupling of to do the engaging of one node. This is different from what we are going to do, because there we were not scaling masses, we were not scaling the momentum, we were not scaling the conformal dimension, while instead, when you do the holomorphic decoupling, you scale together with the mass also the gauge coupling, keeping fixed the new dynamical scale of the theory. Okay, so this is what happens. Now, what's the phase of these irregular vectors? The irregular vectors will bring will bring with the stress energy tensor an OPE. Let me write it directly like that. Okay, call it the irregular in Z, which corresponds of having higher poles, Z to the K plus 2, higher than the ones that you usually find in the OPE for the primary fields. The primary fields, they have an OPE with a stress energy tensor which is a quadratic pole. Now instead, the game is to have irregular vertices which have an OPE with a stress energy tensor with an higher polarity structure. Now, of course, this should correspond to something which is coherent with the Virasoro algebra. So indeed, you can prove that I can take states in the Virasoro algebra, let's call them I, N, which are where the modes which are diagonal, instead of being L0, are Lk for k running from n to n. Okay, for n equal to 0, of course, I go back to the case of the primary, and this corresponds to have here a quadratic pole. Then, of course, you have to say what happens of the higher ones. Well, they are not generated, so they are 0. Lk of In equal to 0 with k greater than 2n. Okay, then from now on, the rest should be fixed by conformal invariance, and indeed it is. It is because, okay, we can introduce some parameterization and give the rest of these operators, let's call them Lk with Z from k, okay, from k plus, here it is. Let me write it like that. K equal to 0 to n minus 1, Lk plus 2 again. And these are differential operators in the lambdas, okay? So they will start, they will contain the derivatives with of lambdas such that they satisfy the Virasoro algebra together with the LKs which are already diagonalized. Good. So this can be fixed by conformal invariance, although there are some ambiguities for higher irregular states until the irregular state is of small dimension. The thing is solved and classified. For irregular states of higher rank, there is still the classification and the study of these states is to be finished. So there is not a complete systematics yet of these states. Of course, you create these higher singularities by colliding primary fields. So it is an amusing exercise to start from the OPE of the stress energy tensor let's say with two primary fields and collide. This has a given expansion delta 1 z minus z1 squared plus delta 2 z minus z2 squared. Then there are the lower order terms, and then you start colliding z1 and z2, but mapping to infinity at the same times delta 1 and delta 2 in a particular way. If you do it, you show that you generate through collision z1 to z2 and scaling in particular way, scaling delta 1 and delta 2, you can generate here, let's say, a quartic singularity.
Why don't you send, from the PhD side, why don't you send two masses to infinity? Couldn't I just decouple one?
I mean, indeed, that's what happens because the square of the what happens is that you map to infinity the okay, in the AGT correspondence you take the two masses corresponds to a linear combination of the momenta, okay? And so when you split that, when you map one mass to infinity, indeed you're mapping the two dimensions to infinity, keeping the difference of the two momenta to fixed. Then the yes, of course, in order to do that, you have to keep fixed a combination of the mass times the gauge coupling, so that you redefine a fixed scale, which is the yeah, exactly. You scale with, let's say, the difference between the two. I mean, so I can do this. Then something else that I can do at this point is instead of killing some of these scales and reducing this amount of irregularity. Okay, of course, if I reduce by 2, I find that the irregularity is just reducing n to n minus 1. If I reduce 1, that corresponds to going to a state which is half integer irregularity. So it is a reduced singularity. So this corresponds to scale the second mass. Okay? And indeed, it corresponds to bringing the quadratic, the quartic singularity down to a cubic one. Okay? If you compare with the formula of phi 2, which I told you before, for the pure matter case, you see here indeed there is a cubic singularity. The other one, which looks a simple pole, when you go at infinity, is again a cubic singularity, but sitting in the other page of the Riemann sphere. Very good. So, in a toy model, which is the one in which we consider the the BPZ equation, this confluence corresponds to the confluence of hypergeometric functions. Confluence of hypergeometric functions, indeed, you take the f to 1, which you know has this structure. Okay, you have two Pochamers above and one Pochamer below. And when you do confluence, you map beta to infinity, you kill one Pochammer, you redefine the variable, and you stay with a function which has only one Pochammer above, one Pochammer below, which is called f11, or also Whittaker function, or trichotomy functions, very good. You can reduce the singularity and go into Bessel functions. Very good. So, we want to understand what is the next case, but maybe we can stop for 5 minutes before a second part of the lecture. Hello? Okay, very good. Okay, so let's start over and try to unify in some picture what we understood. Okay, so we can look at the structural singularities of the Seiberg-Witten curves of the theory, of the gauge theory, and we notice that we can start from 4 regular singularities and start colliding for example, this is an f equal to 4, and this is an f equal to 3. Now we can indeed realize an f equal to 2 in 2 ways, or we reduce one singularity, or we collide the other two. This corresponds in the brain picture, or to realize the theory like that, the symmetric realization, or the anti-symmetric, the non-symmetric realization is this one. Then we can otherwise go, these are so the two possibilities for NF equal to 2, or we can now have one reduced and one non-reduced irregular singularity, NF equal to 1, or two reduced singularity, which is pure super Young-Mills. These boxes are telling you what happens to each singularity. Okay, the index of the singularity in the quadratic differential, which makes the Sever-Witten curve, or from the safety side, the leading order term in the OP of the state that you're inserting at the point with the stress energy tensor. Yeah, the moves are or collision or reductions. These are the two possibilities. Of course, you know that in this picture there could be other possibilities. Let's make this 6 and 2. A collision is breaking two singularities and throw them one against the other to form a quartic. From the field theory point of view, is integrating out of one mass. Okay? So it is a, remember, sorry, is picking, for example, one multiplet and bring it to infinity, okay? And this is and this is the way in which you realize NF equal to 4 from NF equal to NF equal to 3 from 4. One is this. The other one is the reduction of the singularity. Okay, so passing, you remember, from a quartic singularity to a cubic one. Very good. But I can make worse things. Okay, I can bring the situation to have a sextic singularity. And then, out of this sextic singularity, I can do two possibilities, or reduce the sextic singularity to a 5, okay, which corresponds, by the way, to bringing this NF equal to 2 and do some strong coupling limit, okay, down here, where I collide a 3 and a 2. So there is also an error which goes like that. Or I can triply collide and go to singularity of degree 8, which is colliding these two. Okay, very good. And then there is another possibility of going to a 7. Okay, which is also here. Okay, these theories below are Argyll-Douglas theories. Okay, you can prove, I mean, you can open any paper on Argyll-Douglas theories, and you find that these are indeed the degree of the singularity of the Sever-Witten curve at Argyll-Douglas, in the Argyll-Douglas points. Okay, so this is called H2, H1 prime, because there are two realizations also that corresponding, of course, if you are taking the strong coupling limit out of one of the two realizations of the NF equal to 2, and H0. Okay, very good. So we have all the spectrum of gauge theories of SU2 with fundamentals. Very good. So these are this is the scheme by which we would try, by which we will have the possibility of solving the differential equation dz square psi plus the quadratic differential psi equal to 0. Okay, this object here is obtained as taking the classical limit okay? Or, okay, C going to infinity limit of the partition function of Nekrasov full 1 with surface operator inserted divided by the one without. Surface operator. Okay, so we have a machine very complicated, but which gives me materially the solution of this wave equation. Now, this wave equation, beyond the hypergeometric case, does not have a solution in which I write the coefficients in a closed form. Here, the way I should do it is a bit complicated because first I have to do instanton counting and then take the classical limit. But this in principle is giving us a recipe to build this solution as a function of which I can give all the local expansions all the coefficients of a local expansion in a closed form. Of course, it is harder and harder to write down the thing because computing all the combinatorics here is hard. But in principle, I have a closed recipe to write down the thing. I mean, before this approach, for example, ready for four singularities, which are the case that we have there, the way of solving the differential equation was by approximation using a method called a continuous fraction method or lever method. It produces a solution, but through a recurrence relation. Instead, this, in principle, is a direct determination of all the coefficients. Let me say more. One can study the structure of the convergence properties of the Nekrasov partition function. And one finds that the expansion in the instanton coefficient, the instanton counting, is a convergence with finite radius of convergence if the theory is superconformal, and with infinite radius of convergence if the theory is obtained by decoupling. So it means that then we expect that the numerical properties of convergence of this series, of this representation of the series, is very good, and indeed it is very good. Now let's make very short an application of this. And now this it is just like a journal club review. Okay, so I wanted to use this to say something of some other problem where I find a similar equation and I wanted to bring home some result out of this. Let me notice that when I have the possibility of computing all the local expansions, I also have the possibility of computing explicitly the connection formulas connecting the doublet of local expansions around the plane. And this is crucial for the kind of applications we have in mind. So the kind of application we have in mind is to black hole perturbation theory. Now let's make the story very short. So black holes are particular, very symmetric solutions of the Einstein equation. They are so symmetric that when I study linear perturbation around them, so I linearize Einstein equations. These around black hole solutions. You can have in mind some Kerr black hole, but also some Kerr black hole in de Sitter or an anti-de Sitter, with de Sitter or anti-de Sitter boundary conditions, okay? Separate. And since they separate, it means that I can study probably the second order equation, which I will find. Now, the thing can be done explicitly by splitting the wave function, which now depends on the two non-trivial variables, let's say theta and r, after I fix the mass of the black hole, maybe the spin of the black hole, etc., and the two cyclic coordinates, let's say time and axial, the axial direction where the Kerr black hole is spinning. I'm thinking 4 dimensions, but this can be done also in higher dimensions. It has been done. Okay, there the difference between what I'm saying and what happens is that you have to use equivalent gauge theory instead than a single node one. Okay, so I expand my partition, my wave function, therefore, as an integral over the frequency. I have the sum over the quantum numbers, e to the I phi m plus I t omega. Sorry, I'm writing very, very badly. Let's write better this ansatz for the wave function of the fluctuation of the metric. This might hold for the fluctuation of the metric, but also for the for some background field that you want to study in the black hole. Suppose you want to solve a Klein-Gordon equation or things like that. Well, the symmetries of the black hole solution, which means that there exists a particular conservative charge induced by a conformal Killingiano tensor which constrains the geometry, such that this wave function separates into factors. One factor r, which depends only on the radius, and a factor which depends only on the cosine of the angle. One for each quantum number. I don't write them, but of course these still depend on omega, m, and l. And each of these two factors, because separation of variables, satisfy a differential equation of second order. Okay. So what happens is that this differential equation turned out to be of Hoyne type. In some parameters which have to do with all the gravitational background where I'm studying my problem. Notice that it happens for both the terms. So I can solve this factor here is called spherical harmonic, and it generalizes to axial symmetry, spheroidal harmonic, it generalizes to axial symmetry the spherical harmonics that we are used to used to analyze the Schwarzschild case, and are fixed by asking regularity of the solution of the differential equation at the two extremal value of the cosine plus or minus 1. This condition fixes in terms of in terms of instanton counting of some quantum periods in the instanton counting, the separation constant between the two sectors of the theory. The other one instead stays as a known equation in the radial variable that I have to study. Now, physically, what one finds is that let's take the general case. Let's say the Kerr de Sitter case. Black hole, four-dimensional, of course. No? Okay, now I have suppose I draw here the half line of the radius. I have an inner horizon, an outer horizon, a cosmological horizon, and then somewhere here an unphysical horizon, which is sitting there. So 1, 2, 3, 4 regular singularities. Very good. So I can use all the machinery that I built to solve explicitly these Euler equations to give the solution, for example, of a problem of emission from the outer horizon of the black hole and absorption, let's say, at the cosmological horizon, which means basically looking at the possible quasi-normal modes, so the modes, the resonance modes of this black hole. Of course, this exercise can be done also in the case in which it is just a Kerr black hole. In the case of a Kerr black hole, what happens is that the unphysical singularity hits the cosmological horizon, and pure Kerr, at infinity, I have an irregular singularity. So, when I kill the cosmological constant, the Euler equation becomes a confluent Euler equation, of which I can study propagation and connection formulas, which are important to tame the emission spectrum from one singularity to another through to predicting the reflection and transition coefficients with the NF equal to 3 gauge theory. I mean, it's a machine which works. You can make computations. Let's try to finish this cartoon part by stating a few results, a few concrete results. For example, I can compute let's take the Kerr black hole. I can use this technique to compute the gray body factor of the black hole. The gray body factor can be computed by taking the inverse of the modulus square of a particular connection coefficient, the one which relates the purely outgoing wave function to the purely outgoing wave function at infinity, and that computes to any value in the frequency the gray body factor of the black hole. When the frequency is zero, so the static gray body factor corresponds to an hypergeometric limit of the of the confluent Euler equation. And indeed, it was computed earlier by Maldacena and Strominger in some paper in the 90s. Okay, so we generalized to general to general values of omega. All the formulas are given in terms of gauge theory objects. Okay, so there is all a non-trivial dictionary to connect the gauge theory computation to the CFT parameterization and then to the gravitational dictionary. Okay. Okay, so you can do okay. So let me say something. Of course, I can compute now also the resonance. I was saying I can compute the resonance mode of the Kerr black hole, and these are given in terms of the solution of some quantization condition for the of the period of the several periods of the gauge theory. Now, these quasi-normal modes can receive correction at next level in the perturbation theory. So I can do quadratic perturbation theory to the black hole and take the next two leading term. Now, the next two leading wave function, the one which gives what are called the quadratic quasi-normal modes, so the normal modes coming from summing the effect of two copies of the linear perturbation plus the interaction, still come in the form of, let's say, a Noin differential operator acting on the perturbation at second order, which has to be saturated with the perturbation at first order, I mean, with the quadratic expression of perturbation at first order. This comes by the standard second order perturbation theory. But still, so you see that it is a Noin equation, an inhomogeneous Noin equation. So you can use the gauge theory, all the machinery, to compute the green function of this differential operator and solve also this equation. So the answer is yes, it goes beyond the linear perturbation. Well, the gauge theory, I think, is something that sooner or later we should abandon. Okay? Why? Because it is a way by which we reach some combinatorial formulas for abstract differential equations. But I mean, if there is a mathematician who comes and tells me, I mean, how to solve a differential equation in these terms, without telling me that the sum over Young tableaus comes from the gauge theory, I mean, I'm happy to. No? Better, I would like to have a mathematician who tells me why the hell it is important to solve the theory before taking the classical limit. I have in mind the fact that the quantum theory should have been harder to solve. And instead, the hint coming from here is that the quantum integrable system is simpler to solve in closed form than the classical one. This, I mean, for me is a very stimulating question, no? Because I mean, you thought that classical physics was easier than quantum one, and instead it seems that it is not like that. That quantum Liouville theory is simpler than its classical limit. Okay, so I mean there are other things in black hole physics that techniques, but okay, we can discuss privately in the next week with some of you who will be still here to okay to deepen the topic. Okay.
Thank you, Giulio.
Yes, of course.
How much can you push the individuality? Can you statement that all the observables in the for the entropy theory are dual to reveal, or there's some
Well,
origin not known?
I mean, it has been done for surface operators, for Wilson and Toft loop operators. Everything has to be BPS, of course. But higher rank, as we were discussing yesterday, has some checks, but I mean the complete classification of the conformal blocks on the W algebra side is not known. And I mean, less BPS observable, I don't know. I mean, I think that at a certain point should break because I mean we don't believe that the entire physics of the four-dimensional game theory is given by a two-dimensional CFT, but that a particular BPS sector is described by this dual theory. Ah, sorry. Yes. The existence, look at it classically, the existence of the Killian tensor corresponds to the existence, okay, take the problem of the motion of the particle in the four-dimensional space. We have the axial vector, we have we preserve the energy, we preserve, of course, the four momentum. These are three. One which is another quadratic combination of the momentum with something which depends still on the space-time coordinates. The object which forms this other quadratic conserved quantity is the Killing-Yano tensor, the symmetric Killing-Yano tensor. Now, this classical, analyzing the classical mechanics in the background, you can prove that in the case in which that Killing-Yano tensor exists, this goes to also the existence of differential operators which commute with the wave equation of the theory. Okay, when you say that classically p squared is conserved, okay, you're saying that the covariant derivative of the metric itself is zero, no? Very good. So this also happens if you have another second conserved charge, which is quadratic. Now, this quantum mechanically goes to the box operator, okay? And this is the equation you want to solve, okay? the existence of the Kilian tensor gives a differential operator which commutes with the box operator. Okay, and the existence of this conserved quantity, of course, at the classical level tells me how to separate the Hamilton-Jacobi equation of the classical motion, and when you promote to fluctuation of the field, it becomes the separation of the differential, the possibility of separating the solution of the differential equation. So these are symmetries which are there in the given black hole background. And okay, this has been also generalized to higher dimensions, where there will be more conserved charges. I think that there are generations of gravities which have been studying very symmetric solutions also in higher dimensions. By now we stay in, I contain myself to stay in 4, which is complicated enough. Okay. Ah, okay. Okay. So. Okay. 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 So you want. Okay. So your question is about an holographic dual. Okay. Okay. Now I understand what you wanted to know. No, the symmetry still it has still to be a global symmetry of the holographic dual, of course, and so this will be conserved quantities there. The point is how you project holographically, let's say, the motion in the you have to see it from the boundary conditions, no? It is you can use this technique. This has been done, for example, by Grassi, Jossa, and other people to compute the thermal partition functions, thermal point functions in the ADS black hole background, and then they've been carrying it to the three-dimensional CFT. They have some computation for ADS5 and the CFT4. Yes, yes, the background. Yeah, in the I mean, there are some results that are out in the literature on this topic. Of course, the four-dimensional one will have a dual of fluidodynamical type. You have to take there. You can tame the large radius of the black hole, which has to be taken together with the large spin, like in a double scaling limit, and this produces the hydrodynamic limit of the spectrum of quasi-normal modes, and this can be mixed with some computation of characteristic frequencies of the fluids computed from Navier-Stokes equation. This was a computation done by Pufu and other people. I cannot remind the other authors. And we matched some of these hydrodynamical modes with some numerical predictions they had. And we found that the series that we can write down of rescaled quasi-normal modes of in the hydrodynamical limit, they have very strong numerical convergences, and I mean we get 7 digits without any problem while with the first corrections while they were computed the first 2, 3. Okay, so numerically at least the method is competitive. And then, I mean, the problem, what is the problem? Is that every time you have to compute instantaneous until a certain point. And then, once you finish the computation, you take the classical limit and you see what you stay with. If you are not happy because you wanted one term more, you have to add other boxes, do the computation of the next terms, and bring it back. It's another stuff. With the Mathematica, you can do it, but it's still hard. I would like somebody to come and tell me the combinatoric you have to do does not pass from this limit, but maybe it has to pass through there.
Very good. So let's thank Giulio again.
No, well, let me thank the organizers of the as the last speaker. I take the freedom of thanking the organizer of this Focus Week for having organized such a strong program that I see all of you have been able to survive. So very good. Thank you very much. I invite you to clap the organizers.